Hi, I'm Nadine Kabengi. I am an associate professor in the Department of Geosciences, and I have a joint appointment in the Department of Chemistry. My work looks at the fate and transport of contaminations, both environmental and anthropogenic, and straddles both disciplines in a collaborative and interdisciplinary way. Global climate change is the result of and will impact the interactions of humans, society, and the multiple interconnected Earth systems that control our environment and our life, really. It is therefore important to get all disciplines that tackle each of these domains individually and interdisciplinarily on the same page, so we don't overlook any aspect of the issue as we work toward creating solutions and a better environment for ourselves. Much of the work we do in my lab looks at the fundamental chemistry of capturing CO2 and sequestering into subsurface geological system. How will CO2 then react with Earth-abundant material, such as silicate material? Will it potentially enhance their weathering or dissolution? And if so, what problems are we expected to face? Will we release metals from these minerals? Conversely, can we tweak the chemistry to take the CO2 and form new minerals? So my research looks at all these questions, and then we work collaboratively with other disciplines, me and my students, to try to answer all these questions. Cities in general, and Atlanta particularly, are prime examples of hubs where the interactions underlying global climate change intersect and are amplified. Atlanta is also a prime example where many of the changes and the solutions needed to lessen the impact of climate change will have to be deployed. For instance, there are efforts to reduce the urban density and the net emissions from transportation, such as the expansion of the public transit system, MARTA. But then some consideration have to be taken. For instance, we have to examine the stakeholders' response to these efforts and the public response to such an expansion. Current students are the generation responsible for stopping the bleed. They will come of age and mature economically, professionally, and personally in a global setting that is defined by the issue of global climate change. They must protect the environment and put in place sustainable practices, live with the potentially compromised health if the air, soil, and water qualities are not protected. They will benefit from developing skills that will be in line with local and global economies that will prioritize career involved in the global climate job market. First and foremost, I would urge every student and every member of this community to get educated on the topic and demystify some of the basic concepts that will be increasingly at play over the next years and decades. For instance, removing CO2 from the air will require the deployment of new technologies. And there's a general anxiety anytime a new technology is introduced in the public space. Or sequestering CO2 into the deep subsurface may elicit fear and general misconceptions about the safety and the security of the process. So definitely familiarize yourselves with these new concepts and then learn to not be scared of them. Secondly, I would urge you to actively participate in personal choices to reduce the net overall emissions, be it from the energy usage, food choices, transportation, and lean toward more sustainable choices as much as possible. And thirdly, participate in an intentional and sustainable general advocacy to inspire change at a larger scale, be it in your dorm, your apartment complex, your campus, with friends, family, your representatives. Topics could be as broad as pushing for more recycling, or as narrow and as focused as electing those who address this important issue in their politics. Mitigating the impact of global climate change will necessitate the deployment of new technologies and using shared Earth systems and spaces. In this case, attention to the social dimensions, not only just the physical dimensions, such as equity and environmental justice, will be key, as historically and typically, communities in lower economical brackets tended to pay a higher negative price and are generally heavily impacted by negative societal choices. Additionally, and perhaps more intuitively, there must be a synergy that exists between all the physical sciences that are working to solve this problem. So sciences that tackles the interconnected environmental domains, such as air, water, soil, and geology. The general consensus is that net carbon emissions must be eliminated to avoid exacerbating the significant negative consequences on our climate. And while it is important to reduce and capture carbon dioxide at the source of generation, recent reports have highlighted the need to actively remove carbon dioxide from the environment. This carbon dioxide removal, or CDR, will be essential to reaching global climate goals. So broadly speaking, chemists and geochemists, like myself, are asking themselves what are effective, economical, and secure methods to remove CO2 at a massive scale. This generates follow-up questions such as, do we understand all there is to know about the chemistry and the physics of capturing, removing, and storing carbon dioxide? Do we have the materials that can simultaneously capture CO2, but then turn around and release it easily and convert it? Can we develop these materials on time? And in terms of storage, once we have captured CO2, how does long-term storage look like?